So we're still busy talking about determinants. We'll talk about determinants today, and we'll talk about determinants a little bit tomorrow as well. So I've got here fact 2.7, which was something that we discussed yesterday. And fact 2.7 basically says if you've got three matrices A, B, and C, and these matrices A, B, and C are almost identical, right? In all the rows except one, the entries are the same. And then in the pth row, the entries in C are just the sum of the entries in the pth row of A and B. Then we can calculate the determinant of C, and the determinant of C is just the determinant of A plus the determinant of B. And we proved this yesterday. We wrote up an explanation. Basically, we just expand to calculate the determinant. We expand along the pth row. And we noticed that the minors in all three of these matrices in the pth row are the same because the minors are identical. The only place where the matrices are different is in the pth row, but that's the row that you ignore when you're calculating the minors. So what we're going to use fact 2.74 is to prove or explain fact 2.8, right? And fact 2.8 is the last fact about elementary row operations. So yesterday we spoke about the first two types of elementary row operations. We said that if you've got a matrix and you scale one of its rows by a non-zero scalar k, then the determinant is also just scaled by k. And then the other thing we said was that if you've got a matrix A and you exchange, you swap two of its rows, then the value of the determinant changes by a factor of -1. We didn't actually explain that, but we'll see it as a tutorial problem next week. So this is the last thing. If you take the last elementary row operation, which is that you take a scalar multiple of one row and you add it to another row, the claim is that it doesn't change the value of the determinant at all, and we'll see why. It's going to rely on 2.7. So let's just write up a little bit about this. So what we're claiming is that Bij is going to be equal to Aij. Sorry, this is still a bit loud, I think. So Bij and Aij, the entries are going to be completely the same in all the rows except one. So let's say it's row P. All I not equal to P, and Bpj will be equal to Apj plus k times by Aqj, right? So this is the result. These will be the entries in the matrix B if we've added k times by row Q to row P. So these are the entries. These are the entries of B if it is obtained from A by adding k times by row Q to row P. Is everyone happy with this statement so far? Right, because basically as soon as we understand this, we apply fact 2.7 and we immediately get the answer. So this is the difficult part, just making sure that we understand what's going on here. Yes?
Can you explain again the
Okay, so we've got a matrix A, and the entries here are going to be like A11, A12, A21, and so on. And you've got a matrix B, B11, B12, and so on. And so what we've done to get B is we took the matrix A and we took a copy of one row, took row Q, we scaled it by K, and then we added it to row P. Okay. All the other entries of A we left completely unchanged. So if we are not in row P, if you're not in row P, then the entries in the matrix P and the entries in the matrix A are exactly the same. If you are in row P, then the entries in the matrix B were just the original entries in that row plus the entries from the qth row scaled by k. Okay, so that's what's going on over here. Now we use fact 2.7, right? If you just take a look at what we have there, this over here seems to meet the requirements for fact 2.7. All the rows are identical except one row, and in that one row, it looks like the entries in this matrix are the sum of some things. So let's just think about what fact 2.7 says. Fact 2.7 says the following. By fact 2.7, yeah, all right. I mean, like, that's really convenient because I was worrying about glare on this screen, but it is sort of weird. Okay, so by fact 2.7, the determinant of B will be equal to the determinant of A plus the determinant of some, oh, oops, that's supposed to be a plus sign, plus the determinant of some fairly strange looking matrix. It'll be a determinant of this matrix here. It'll be a matrix where all the entries except the pth row are the same. So in fact we can write it like this: A11, A12, A1n. And then in the pth row you've got A row P1. Oh, sorry, not. You've got KAQ1, KAQ2, KAQN, right? So that's happening in the pth row, and then somewhere we have the actual qth row. And then this goes all the way down to A N1, A N2, A N. All right. And the claim I'm going to make is that this matrix over here has got a determinant of 0. And it's got a determinant of 0 because two of the rows, row Q and row P, are scalar multiples of each other. Right? So that's something that we said yesterday. If you've got a matrix where two of the rows are scalar multiples of each other, the determinant of that matrix is equal to 0. So this bit here is equal to 0. Why is it equal to 0? Rows P and Q are scalar rows P and Q are scalar multiples. So that just tells us that the determinant of B is the same thing as the determinant of A. Is everyone happy with this? Yeah. Okay. So I think then what we can do now is we can work through an example. I'll do the first example and then you can do the second example. So here's the first example. We're going to calculate the determinant of the following matrix. So we're going to say evaluate We're going to evaluate this over here. Now this is a fairly small matrix. It's a 3 by 3 matrix. We could actually calculate the determinant by expanding along the row or expanding along the column. But I'm going to show how we might calculate it using Gauss reduction instead, because Gauss reduction can be applied more easily to larger problems. So if we want to evaluate this, I claim that this is going to be equal to 2 times by, and the first thing we do with Gauss reduction is we just scale so that the top row is equal to 1. So if I've taken out that factor of 2 from the first row, I just put it over here. Yes? Oh, that should be a 7, yes, sorry. Now I'm going to subtract multiples of the first row from the second row and from the third row to make the entries in that first column underneath 1, make those entries equal to 0. And that's not going to change the value of the determinant at all. So this is equal to 2 times by. So we get 1, 2, 3. 2 minus 2 times by 1 is 0. 6 minus 2 times by 2, so 6 minus 4 is 2. 5 minus 2 times by 3, 5 minus 6 is minus 1. 1 minus 1 is 0. 2 minus 2 is 0. 7 minus 3 is 4. And this is now an upper triangular matrix. So the determinant of that matrix is simply the product of everything on the diagonal. So 4 times by 2 times by 1 is just 8. And then there's a 2 outside. 8 times by 2 is 16. And we're done. Right? This happened to be a very quick example. We only had to do really sort of one step of Gauss reduction. And then you immediately get this very nice matrix. Yes?
The first step, you took out the 2.
Yes.
Why didn't you try the 6 in the center?
For the first step, I took out the 2. So I took out the 2 from, I took this row here. The difference between this row here and this row here is that I've scaled by 2, right? So I've got to correct with that 2. So, we haven't changed that center value of 6 at all. That's, oh, no. So this 2 is a result just of scaling this matrix, right? In some sense, we've scaled that first row by a factor of a half, so we know that we've changed the value of the determinant by a half. So to correct for that changing the determinant by a half, we multiply by 2. All right, yes?
Why does the scalar only affect the 1 row and not the entire matrix?
Why does the scale? Okay, so that scalar affects only 1 row, not the entire matrix. That's something that we explained, I think it was yesterday. But the basic idea is that when you calculate a determinant, you can choose a row and you expand along that row, right? And then you have smaller minors. And so the point is, if we were to expand along the first row, and if we were of that top matrix, or if we were to expand along the first row of the matrix in the second line, the only difference is that the coefficients have changed by a factor of 2, right? So we only need a 2 to correct for that. This is maybe actually a good point, because it's I guess a common mistake that people make, or that I've seen made before, which is that if you are taking 2 and you just multiply it by a matrix, right? Then that 2 multiplies every entry in the matrix. If you are multiplying a determinant, it's equivalent to only multiplying a single row, right? So this is a mistake some people make where they confuse, does this 2 multiply the entire matrix? Yes, if you're multiplying a matrix. Or does it affect only a row? Yes, it only affects a row if you're taking the determinant of that matrix. So just be careful about that. That's something which does occasionally trip people up. Right. Yes?
If you were to take on 2 common facts, the middle row was 2, 6, 10, so you would take on 2 here. Would it be the 2 on the front would be 4?
Yeah. So if you want to keep taking out, over here for example, let's say I took out this as a common factor. I'd write down 1, 2, 3, 0, 1, negative a half, and I'd put another 2 over here. And over here I could take a 4 out, write 0, 0, 1, and I'd put another 4 here. And then the determinant of this would just be 1, because you'd just have 1s on the diagonal, but now you'd have a 16 out here in front. So yes, if you perform many row operations, you just keep adjusting the determinant by the appropriate factors. All right. Any other questions about this? Yeah. When you're taking out another scalar, yeah. So let me actually let's just do an example, and then maybe we can make this very clear. So this is So here, just as a response to some questions, let me quickly make up some example that we might think about. So let's say you've got 2, 4, 6, and over here you've got, say, 3, 12, minus 15, and then you have, I don't know, 0, 0, 1. Let's make lives very easy for ourselves. Okay. What you could do now, if you took out scalars from the first row, let's say you take out that factor of 2 from the first row, you would write down 1, 2, 3, and then you'd have 3, 12, negative 15, 0, 0, 1. And then what we could do is we could take out a factor of 3 from the second row if we'd like. So we'd have 2 times by 3, 1, 2, 3, 1, 4, minus 5, 0, 0, 1. Okay, and now we can do our Gauss reduction if we'd like. We'd say, so this is 2 times by 3, that's 6. 1, 2, 3, 1 minus 1 is 0. 4 minus 2 is 2. Minus 5 minus 3 is minus 8. 0, 0, 1. And then this is upper triangular. So its determinant is just the product of the things on the diagonal, in this case 2. You get 2 times by 6. That's equal to 12, right? So that's, I guess that's what's going on here, right? If you've got to take more scalars out, you just keep taking them out. And you have all the scalars, all the factors at the front. Yes?
Just want to confirm there are adding or subtracting in a row, but in multiple of the row, does it change anything?
It doesn't change anything. So if you add or subtract, if you take over there, for example, to go from this matrix to this matrix, we took row 2 and we subtracted 1 times by row 1. Doesn't change the determinant. So when you add or subtract rows to other rows, your determinant stays the same. All right. Everyone happy with this example? So let's take a look at a more complicated example. And my suggestion, in fact, let me write it down and then I'll tell you what my suggestion is. So let A be So we have this matrix A. It's a 4 by 4 matrix. It doesn't have any zeros in it. We're going to try to calculate the determinant of this matrix A. Now you can do this 2 ways. You could either just immediately try to do an expansion straight away. Right? That's a terrible idea. It's a lot of work. You'd expand along a row or a column. So you'd end up with a sum which has got 4 terms in it. Each of those terms would require evaluating a 3 by 3 determinant. And to evaluate each of those 3 by 3 determinants, they'd each be different, you'd have to expand along a row or a column. So you'd get 3 more sums, or you'd get 4 sums of 3 terms. You'd end up doing a lot of work, right? So don't immediately jump in. I think that would be a bad way to do this. The other way to do this might be to Gauss reduce this completely, all the way down until you've got a nice upper triangular matrix, keeping track of all the operations you perform. And then once it's in upper triangular form, you just multiply the elements on the diagonal, and the product of those elements on the diagonal gives you the determinant, and then you adjust it by all those factors that we pulled out. So those are the sort of 2 extremes. You could also do something, and this is what I would suggest for this particular problem, which is just in between. Do 1 step, or maybe 2 steps of the Gauss reduction, just so that you've got one nice column where you've got a 1 in the top and a bunch of zeros underneath it. And then if you wanted to calculate the determinant of that matrix, it's fairly reasonable, right? You can just expand along that row or that column with all the zeros, and then it's very easy to do the calculation by expansion. So you've got 5 minutes. Go ahead, try to calculate the determinant of this matrix. So if we just do just the sort of first step of Gauss reduction, right, which would be to make all the entries underneath the first pivot equal to 0. This is already, just this one step of Gauss reduction, this is already enough work, or this is already enough progress to reduce the amount of work needed to calculate the determinant enormously, right? We could now, if we wanted to calculate the determinant, we could now expand, for example, along that column over there. So we'd end up with 1 times by the determinant of a 3 by 3 matrix, plus 0 times by something, plus 0 times by something, plus 0 times by something. And then you don't have to worry about those other terms. So just doing this first step by Gauss reduction immediately sort of reduces the amount of work in the expansion by a factor of 4. So at this point here, you can now either choose to expand along this column to complete the problem, or you could continue doing Gauss reduction until this is up and running. Expansion along that first column. So the nice thing about the expansion along the first column is that you just get 1 times by a 3 by 3 determinant, and all the other minors are multiplied by 0, so you don't have to bother calculating them. And then this 3 by 3 determinant, again, it's reasonably easy to expand. There's a 0 in the first column, so if we expand along the first column again, we just get 2 by 2 minors to evaluate. And that's fairly straightforward, and you do this calculation, and you get negative 200 over here as the result of this calculation. Is everyone happy with what we've done over here? All right. Okay. So this is, I guess, just something which you should know how to do. You should know how to calculate determinants of 3 by 3, 4 by 4 matrices, and so on. This is going to be really important a little bit later on in the course when we start speaking about eigenvalues and eigenvectors. To calculate eigenvalues and eigenvectors, we're going to have to take determinants, but we'll come back to that. For now, let's keep talking about some of the properties of the determinant. So I want to start with the definition here, and this, I guess, is something which I mentioned yesterday but didn't actually write down. So the transpose. So the transpose of a matrix A, and we write it A and then this sort of capital T as a superscript, that capital T stands for transpose. The transpose of a matrix A is written A transpose and is found or generated or made, let's say, found, no, generated. You generate the transpose of a matrix by exchanging the rows and columns of a matrix. So let me just show you a very simple example of the transpose of a 3 by 3 matrix so that you get the idea, right? So for example, if I took 1, 2, 3, 4, 5, 6, 7, 8, 9, right, I take this matrix over here and I take the transpose of this matrix. That's the same as the matrix. Now the first row in my original matrix was 1, 2, 3, so that becomes the first column, 1, 2, 3. And the second row was 4, 5, 6, that becomes the second column, 4, 5, 6. And the third row, 7, 8, 9, becomes the third column, 7, 8, 9. So one thing you might notice is that entries on the diagonal will stay on the diagonal. And sort of entries below the diagonal will get flipped, and they go above the diagonal. Entries above the diagonal end up below the diagonal. So this is just the transpose. You just exchange rows and columns. All the rows become columns, all the columns become rows. And what I said yesterday, well, I think I said yesterday, I don't remember if I said that if you take the transpose of a matrix, the determinant of that matrix doesn't change. So let's just write this down as well. I think that's fact 2.9. You take the determinant of A transpose, that's the same thing as the determinant of A. And I'll explain why this is true for the 2x2 case and the 3x3 case, and then you can maybe sort of just accept that it will work for the 4x4 and 5 case in a similar way. Right. So let's take a look at the explanation here. I'm starting with the 2x2 and then working up with the 3x3 case and so on, because we know that one of the ways we defined the determinant was we defined the determinant recursively. So we start with the 2x2 case. So in the 2x2 case, if you take the determinant of a matrix A, B, C, D, that's equal to, right, you take product on that diagonal with a positive sign, product on this diagonal with a negative sign, so that would be AD minus BC, and it's pretty easy to check that if I now write down ABCD, if I write down the transpose, right, you take that with a positive sign, that with a negative sign, okay, and you get exactly the same thing. Right, so for a 2x2 matrix, taking the transpose doesn't change this at all. Right? The things that were on the diagonal with a positive sign stay on the diagonal with a positive sign when you take the transpose. And these two entries which were the other diagonal, they're still on the other diagonal. You've changed the order that they're written down, but that doesn't make a difference. It doesn't matter what order you multiply things in. Okay. So the determinant of A transpose is the same as the determinant of A. What about the 3x3 case? Right, so the 3x3 case. This was the 2x2 case. What about the 3x3 case? So the 3x3 case is a little bit trickier. So let's say we want to calculate the determinant of A, B, C, D, E, F, G, H, I. Okay, and I'm going to calculate the determinant by expanding along that first row. So we'll expand along that first row. So this is going to be equal to A multiplied by EFHI. EFHI. Okay, I suspect I'm going to run out of space. Let me actually just move everything over to the side here. Plus B multiplied by, and then the minor here, let's see, we DFGI. DFGI. And then the last one is C. And that would be DEGH. Oh, I've made a mistake somewhere. Yeah, where is it? Oh, minus B. Yes, of course it's minus B. Yeah, all right. You can immediately tell when you've made a mistake. Everyone is so keen. Like, there's blood in the water. DEGH. Right. So here's a 3x3 matrix, and we've calculated its determinant, and this is its determinant. Look here. So underneath this, I'm going to write the transpose of that 3x3 matrix and calculate its determinant as well. Okay, so underneath this, let's write down a 3x3 matrix. A, B, C, D, E, F, G, H, I. And I'm going to calculate the determinant over here of the transpose. by evaluating, or by expanding rather, instead of along the first row, I'm going to calculate the determinant by expanding down this first column. So I get A multiplied by, so now it'll be EHFI. Minus B multiplied by DGFI plus C multiplied by DGEH. All right. What we have here on the right-hand side, well, these two things are equal, right? Those two things are equal because when we take the transpose of a 2 by 2 matrix, the value of the determinant doesn't change. We've just shown that. And similarly over here, these two things are equal because those little minors are just 2 by 2s, and when we take the transpose of a 2 by 2, it doesn't change. And over here, these are also equal, right? So all the things on the right-hand side are equal, which means that the things on the left-hand side must also be equal. Okay. So because the 2 by 2 matrix doesn't change its value when you take the transpose, the 3 by 3 matrix doesn't change value when you take the transpose. And what you would do now for the 4 by 4 case is you'd say, well, I've got this 4 by 4 matrix. I'd expand along the first row. Then I take the transpose of the 4 by 4 matrix, and you expand along the first column. And all the things in the expansion of the matrix A will be 3 by 3 matrices. And all the things in the expansion of the matrix A transpose will also be 3 by 3 matrices, but they'll have been transposed. But those will all be the same, those 3 by 3 matrices, because we've just shown they're the same, which means that the 4 by 4 matrix doesn't change when you take the transpose. And then you look at the 5 by 5 case, and the 5 by 5 case will rely on the fact that the 4 by 4 case works. And the 6 by 6 case uses the 5 by 5 case, 7 by 7 uses 6 by 6, and so on. Right, so that's the basic idea. If we wanted to do it a little bit more formally, we'd use induction. We're not going to do induction. We're just going to now say, similarly, this holds all the way up. Right? So since 2 by 2 is unchanged, since 2 by 2 is unchanged by transpose, so is 3 by 3. Since 3 by 3, determinant of 3 by 3 is unchanged, so is 4 by 4 determinant, etc. Right? So we'd actually do, if we were in a pure math course, we'd do some induction, we'd show that this holds, but this is the basic idea. Okay. As a consequence of this, and we'll call this fact 2.10, everything we've learned over the last couple of days about rows of matrices is also true for columns of matrices. So, for example, if you swap two rows of a matrix, the value of the determinant changes by a factor of minus 1. Well, if you swap two columns of a matrix, the value of the determinant changes by a factor of minus 1. We know that if you've got two identical rows in a matrix, then the determinant is 0. Well, if you've got two identical columns in a matrix, the determinant is 0. So everything that we've learned for rows is also true for columns. Right? So all previous facts about determinants and rows are also true for determinants and columns. Right. And the way you see this is you just take the transpose, which leaves everything unchanged. You do all your row operations, and then you take the transpose back. Okay, so So let's not worry too much about that. Yes? Yes. So if you swap two rows in a 3x3 matrix like this, your determinant changes by a factor of -1. And if you were to swap two columns, the determinant will also change by a factor of -1. It's just saying that everything you know about rows also holds for columns. Okay. Fact 2.11, very important, but we aren't going to be able to we aren't really going to be able to prove it, although I can actually explain the proof to you. The proof is not so hard. But if you've got two square matrices, A and B are n by n matrices, then the determinant of AB is equal to the determinant of A multiplied by the determinant of B. Okay. You don't need to write down this explanation. We don't really do it, but let me just explain the basic idea. In fact, let's not even bother with the basic idea. If you're interested, come and speak to me afterwards. Yeah. So I think we'll finish off there, and then I'll see you all tomorrow.